This is a video about section 3.3, and section 3.3 is where we start to talk about concavity. So I want to define what concavity is. Concavity is really a description of the shape of your curve. It's not increasing or decreasing necessarily. Actually, sometimes it's both in a region of concave up or concave down. So I think the first thing I'd like to do is just get a feel for what it looks to be concave up, what the curve looks like when it's concave down. So concavity, section 3.3. Now we know that the curve is broken up into intervals of increasing and decreasing, and I think we can naturally see those now. Increasing, 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 critical number, switch. Decreasing, 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 critical number, switch. Increasing all the way out. But the switch for concavity does not take place at the critical numbers. This is a critical number right here. This is a critical number here. The switch for concavity takes place about here. This region, from here all the way out, the curve would be called concave down. It's like a parabola that's shaped downward. And if I were to cover up the other half of the curve, it very much does look like a parabola that turns downward. If I look at the other half over here, we call that shape concave up. So concave down and concave up is really a description of the shape of the curve, not really the increasing and decreasing. In fact, in a region in which it's concave down, you have both. You have increasing and decreasing sections here. So this is going to be a very important point for us. Where does that switch take place? And it takes place at a location called a point of inflection. Critical numbers are not necessarily points of inflection. Concave down, concave down, concave down, concave down, concave down. Nothing happened here. It happened here. Now, that's not the only style of a point of inflection we can have. That's not the only place concavity can change. Here's another type of concavity change. How about we do this? We have a curve that does this. It flattens out for a moment and then does that. Now, this curve I would consider to be monotonic. Monotonic means one behavior, mono. Increasing, 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 and maybe just for a moment f prime is 0, but it increases from here to here and it increases from there to there. So actually it increases throughout the entire domain. So increasing throughout the entire domain, and if I were to do my intervals of increasing, decreasing, I'd say increasing from minus infinity to infinity. There are no real intervals in which we get any changes. But we do get a change in concavity. So if we cover up from that location, you would have to call this region concave down. It's like a downward-facing parabola. If I went and covered up this section, take a look. That's a section in which we would refer to it as concave up. So the switch took place right here, and we will refer to this point as also a point of inflection. So now I know that when we get a flat spot, we don't really call it a flat spot anymore. We call it a point of inflection. Now, points of inflection, like this one and this one, we're going to say that just like we did for increasing, decreasing, you remember the critical numbers were opportunities for change. Change might not happen. In fact, this was a perfect example of that. This is actually also a critical number, isn't it? And did increasing, decreasing change? Not at all. Increasing, critical number, increasing. So critical numbers were opportunities for change, for increasing, decreasing. Points of inflection are opportunities to change concavity. No guarantees that you'll get a change in concavity. And there's one more change in concavity that's worth looking at. Let's take a look at this one right here. Asymptotes. This curve is currently concave up. Then it comes down from here, and it's also concave up. So the asymptote, while it might have been an opportunity for change, we have a region in which the curve is concave up, and then another region in which the curve is concave up, and not a lot happened there. So maybe we don't need to pay attention to asymptotes. I don't think that's true, though. Let's put another vertical asymptote right down here, and this time I'm going to draw this curve, and I'm going to draw this curve. Now, to be concave up, you don't need to see a full parabola. You can see a tiny portion of the shape. Now, they're not really parabolas, but you can see a portion of the shape to know that this is a region of concave up. And this, if you extend it here, this looks like a region, if you had to label it, of concave down. Therefore, vertical asymptotes are also opportunities to change. So the definition of concavity. How do we know when curves are concave up or concave down? Let's talk about that. It's all about the second derivative. Now let me draw you, we'll pick one here. We'll pick concave up. Take a look at f prime for a moment. And I'll draw a few of these derivatives out here for you so that we can try to analyze these. These are all derivatives. They're all slopes of tangent lines all along the way here in a region of the curve that is concave up. And let me read these out to you. Maybe this is f prime equals, let's make it minus 5. This is f prime equals, let's say, minus 3 or something. This is f prime equals minus 1. This is f prime equals minus a half. And finally, we make it to f prime equals 0. Now, over here, I have f prime equals, let's say, positive a half. I have f prime equals positive 1. I have f prime equals positive 2. Now, I realize that f prime went from negative to positive, which is decreasing to increasing. We know about that. But what about how f prime changes? So what is f prime telling us? F prime says this is how your function changes. This is how y is changing. And when f prime is negative, it's telling you that y is on the decrease. When f prime is positive, it's telling you that y is on the increase. Certainly that's what happened. We're on the decrease, f prime negative. We're on an increasing portion. F prime is positive to tell you that it's increasing in that region. But what about f prime itself? What's going on with f prime itself right now? Negative 5, negative 3, negative 1, negative a half, 0, half, 1, 2. F prime itself is constantly increasing. Bigger, 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 bigger. So even though it's switched from negative to positive, overall, I would say f prime just kept increasing on me. From negative 5 right up to positive 2. Just kept increasing. So f prime itself is increasing. And how do you determine if something is increasing or decreasing? Well, f prime is like a brand new function. And if you want to know if this function right here is increasing, you need to look at its derivative. And that would be f double prime. And what would f double prime be in a region in which the function, which is f prime, is increasing? The next derivative is f double prime, and f double prime would therefore be positive throughout this interval. So you have to see f prime as its own function. As its own function, it is a nice increasing function throughout the entire interval. All it wants to do is get bigger. So how do we know that f prime is increasing? By looking at its derivative, meaning f prime, prime again, get another derivative on top of it. And plus would mean that this is increasing. So that says that wherever f double prime is positive, f prime must be increasing. And we've already seen what happens when f prime just keeps getting bigger. We're in a region of concave up. So f double prime speaks the language of concavity. If f double prime happens to be positive, we know we're in a region in which f prime is going up, and the side effect of f prime going up is it lays down a curve that looks concave up. Well, I think you could also imagine that wherever f double prime is negative, that would mean that f prime itself is decreasing. And the implication there is that it must lay down a curve that's concave down. So f double prime speaks the language of concavity, and that is our second derivative. Second derivative speaks the language of concavity. Now, how do you switch from concave up to concave down? Well, you switch from a positive second derivative to a negative second derivative. How do we switch positive numbers into negative numbers? Well, if you have positive numbers and you're trying to get to negative numbers, you must go through 0, right? So I'm thinking that the switch would occur when f double prime is equal to 0. I would say the switch in concavity that occurs when f double prime actually equals 0, and very much like our previous section, also where f double prime is undefined. Now, what's great about this particular section is everything you know about the increasing and decreasing intervals plays a role here, except we're not doing increasing, decreasing, we're doing concave up and down. We're not doing f prime anymore, we're doing f double prime. And that's it. You just need to change the terminology. The tables actually look the same. So, what happens when you get f double prime 0 undefined? You get points of inflection. Now, to really be a point of inflection, you got to see a change in concavity. That would be right here. And by the way, it does say point. So if it says point, I need a coordinate. X isn't good enough. Now, in the previous section for increasing, decreasing, we use critical numbers. Those were just x values. These, we need the coordinates, both the x and the y. So make sure you really call out the point. That's a point of inflection. What else? Flat spots. Here's another point of inflection right here. See, concave down, concave up, concave down, concave up. So those are the two kinds of points of inflection that we would find. What else should we be looking for? Now, in order to be a point of inflection, you got to be a point first, right? Vertical asymptote is certainly not a point. However, a vertical asymptote is very clearly an opportunity to change concavity. So what we need to build our table to find out where the switch will take place, we need the x's for our points of inflection to be slicers. We need our vertical asymptote x's as well to be slicers. So we're back to having to have vertical asymptotes. We don't call vertical asymptotes critical numbers. We don't call vertical asymptotes points of inflection because they're not points. And yet we need them in our table. It's clear that that can possibly get us a switch from concave up in this particular example to concave down in this example. Okay, so here's what we're going to do. Let's build a table. And the table will be the intervals of concave up and down. To do this, you need your slicers again. But this time, the slicers will be points of inflection and vertical asymptotes. So to do that, to find those, I guess the first thing you should do maybe is just do f of x is undefined, but not this kind of undefined. That's a different kind of undefined. Remember, this undefined looks like that. We don't want those. So undefined means we want a finite number over 0. So I guess you could just set the denominator to 0 and find your vertical asymptotes. Get that out of the way first. Second, slicers, points of inflection. And that's where f double prime is either 0 or undefined. And then we'll build our table. So let's get started on a good example. Let's try this problem. F of x is 6 over x squared plus 3. I'm using a good example from the book here. So really, the first thing I think you should probably investigate are vertical asymptotes. And vertical asymptotes occur when the function itself is undefined, and that's when you divide by 0. That's not real, though. That's not a real result. Therefore, there are no real vertical asymptotes here to worry about, even though it's a division problem. So don't have to worry about vertical asymptotes. Let's find our points of inflection. And you'll see that I very carefully make sure they're points by getting both the x and the y. Now, to get the points of inflection, you need the second derivative. This chapter is all about the second derivative. Second derivative speaks the language of concavity. When f double prime is positive, you're in an interval of positive concavity or concave up. When f double prime is negative, it's concave down. So when f double prime is 0, though, that's where the switch might take place. When f double prime is undefined, that's also another spot where the switch might take place. So I can't get that directly, though. I got to go through the first derivative first. So this is my f and this is my g. Make a table. Now, before I really follow through with this, think about it. Do you really need the product rule for this? Or the quotient rule, I'm sorry. And the answer is no. You do not need the quotient rule for this. And here's how you do it without the quotient rule. Take this right here and push it to the top. See, the thing is, the numerator is simply a constant multiplier. It's along for the ride. You don't need the quotient rule. And I think it's going to be a lot easier without it. So f prime equals 6. You're just along for the ride. Chain rule, please. The negative 1 drops down. We deduct 1 from our exponent. Never change the argument. And chain rule dictates the derivative of what's inside as well. What do we get from all this? On the top, I get a negative 12x. On the bottom, I get an x squared plus 3 squared. That's f prime right there. Okay. Yes, I need you to do the algebra to get it right. Make sure it's clean at the end. And that's pretty clean. F prime isn't going to help me. Okay, I need f double prime, and I don't have it yet. So what are we going to do about it? Quotient rule must be done. because that's a function of x. So now I don't have a choice. So this is negative 12x. F prime is negative 12. This is x squared plus 3 squared g prime. Well, that's one big chain rule there, right? The 2, drop it down, deduct 1 from the exponent, always copy the insides, and then multiply by 2x. That's the derivative of what's inside. So what I get here is 4x, x squared plus 3. Now we're not nearly done because you want f double prime, you have to run the quotient rule. The quotient rule looks like this. F prime g minus fg prime all over g squared, right? That is the quotient rule. Let's carefully do this. F prime g minus f g prime, right there. So that's a 4x and an x squared plus 3 all over g squared. What a mess, right? So we really need to investigate what that's all about up there. There's a lot going on up there. But we can do this. Now the first thing I recommend is let's do a little bit of cleanup here. Double negative, right? That's positive. 12 times 4 is 48. X times x is x squared plus 3. And also down below is x squared plus 3, all raised to the 4th power because those two powers multiply. Most important thing to note, do not cancel this with this. And this actually is your typical quotient rule problem. They typically do kind of look like this, and there's lots of temptations to do things you shouldn't do, like cancel those two. In fact, what you should do instead is factor the numerator here. Now, to me, there seems like there's a common 12 at least, or a minus 12. So I'll take a minus 12 out front from here and here. There's also a common x squared plus 3 here and here. So bring that out front, x squared plus 3. And in parentheses or brackets, show me what's left. Now we ripped the minus 12 out, it's out front. We ripped one of these x squared plus 3's out, leaving me with an x squared plus 3. We ripped out a minus 12, meaning divide by minus 12, you get minus 4. We didn't rip the x's out. Okay, so the x squared should stay. Oh, but we ripped this out, so that's gone. It's important to note you really can't solve this problem without doing what I just did, and that is to factor it. You'll see why in a second here. Now, x squared plus 3 to the 4th power, multiplication. Multiplication, you are perfectly within your rights to cancel one of these with one of these. I do not see any pluses or minuses out in the wild here, except for that one. That's just a negative quantity, though. So cancel one of these with one of these. So in the front, I get a negative 12. What's really in this bracket here? Negative 4x squared plus x squared. That's negative 3x squared plus 3. All over x squared plus 3 cubed. There's no question it takes a longer time to get to your second derivative. There's no question that the quotient rule takes more effort. But you have to run through it in detail to get to this point. And to find that hidden quantity in those brackets, this actually will be probably the most important portion of the second derivative right here. So there's only one way to get there correctly, and that's to factor out the common factors, put what's left in here, and then combine them. This is not uncommon. Okay, that's f double prime. We want f double prime equals 0, but f double prime is a fraction. What do? Set the numerator equal to 0. Sound familiar? It's just like we did for the first derivative. The minus 12 doesn't do me any good. We get rid of it, and you get minus 3x squared plus 3 equals 0. Subtract 3. You get minus 3x squared equals negative 3. Divide by negative 3, and you get x squared equals 1. We've got two locations where we will find points of inflection, plus 1 and minus 1. Now, they're not points of inflection yet, unfortunately. To really be a point of inflection, P of points of inflection, I really got to see points. Now, y values are easy. We know where to get our y value from. We get our y value from here. So we got to put a negative 1 in and a positive 1. They're both going to be 1 plus 3 is 4, 6/4, or 2/3. So, 3 halves. So those will be considered our points of inflection. So go back and get the y value, please. Now, f double prime, we also have to investigate when it's undefined. And that's when the denominator will be 0. I don't think that's going to happen, though. Denominator, when are you 0? Take the cube root of both sides, subtract 3 from both sides, and we're right back to where we were before. The square root of a negative number. It's not real. So that doesn't happen. So these are the 2 points of inflection, negative 1 and positive 1. We have investigated the vertical asymptotes that don't exist. We've also looked for f double prime undefined. And now we make our table. So how does the table look on concavity? It's very similar to increasing and decreasing. We put negative 1 here as a slicer. We put positive 1 as a slicer. We do the same thing we did in the previous section, and that's define the interval, which is all the x's less than negative 1, all the x's between 1 and positive 1, negative 1 and positive 1, and all the x's greater than positive 1. We next sample with a representative, and that would be negative 2 here, 0 there, and positive 2 there. And this is all about concavity. So what are we going to sample there? The second derivative is what we're going to sample for concavity. So let's do f double prime at negative 2 to see what happens there. Okay? Where is f double prime? F double prime is right there. Okay? So I got to do some work here. Negative 2 plus 4. Okay. Let me work this out. Didn't have this prepared. So I've got... give me 1 second here. 3 minus 3 times 4 times negative 12. Here's what I'm getting. I got 108 on top and 7 cubed on the bottom. The number's really not what I'm interested in. That's what I'm interested in. Okay, let's do the next one. Let's do x equals 0. That shouldn't require a calculator, right? We put 0 in, we get 3 on top. We put 0 in, we get 27 on the bottom, 3 cubed. So really, the 3's will cancel. We'll get a 9 on the bottom. We get a minus 12 over 9. Minus 12 over 9. So f double prime at 0 is minus 12 over 9, but that's minus 4/3. And this is the only thing I really care about. Now let's put the 2 in. Let's put the 2 in. So if I put the 2 in, I get pretty much the same thing I get over here on the bottom, 343. I put the 2 in, I actually get the same thing on the top. And again, all I care about is concavity. I care about plus or minus. Now, the conclusion here. Remember, we're working with the second derivative. We're not working with the first derivative. This is not a table of increasing, decreasing. It's a concavity table. This is a region of concave up. You can draw concave up if you like. This is a region of concave down. You can draw concave down if you like. And this is a region of concave up. So that's how we do this mathematically, and that is to access the second derivative. and find points of inflection. So we do f double prime is 0, we do f double prime undefined, and we also make sure, if they exist, to pick up vertical asymptotes because they also are required as slicers. We slice up the domain, we pick a representative, we sample the second derivative because within a particular interval that you've found here, the second derivative won't change sign. So it's going to be completely positive throughout the entire interval, so only one sample is needed. Did we get this right? Well, ultimately, the best way to find out is to check this curve, and that is to graph it. So let's take a look at the graph of this curve by going to our little graphing computer again here, our graphing calculator. Now, this particular curve was 6 divided by x squared plus 3. So at the moment, it doesn't look too good, does it? But if we zoom out, we're starting to see things here. Now, it's hard to see the concavity in this curve, isn't it? But our claim is from -1, which is right here, from -1 to +1, we're in a region of concave down. And if I zoom in enough, you can see from -1 to +1, you'd have to agree that if you want to give that a label, that's concave down very much as what we discovered. It does say for all x's less than 1, you're in a region of concave up. Well, let's move over here and put the -1 over there and maybe zoom out a little bit, still stick the -1 over there. And what would you call this region here? Well, if you had to give it a name from -1 all the way out to -infinity, that looks like concave up for sure. And the same thing should hold true from 1 out to infinity. So we look here from 1 on, right there, 1, that also does look concave up. I know it's decreasing, but concave up or down, that is concave up. So we found our regions of concave up and concave down. In order to do so, what you really need to do is find your points of inflection. Specifically, the x values are needed in the table. Find your vertical asymptotes, if they exist. Those are all going to be your x slicers. Slice up your domain, pick your representatives, sample the second derivative at your representatives. The only thing we care about is the sign, plus or minus, and that will tell you what kind of concavity you have. The next video will talk about the second derivative test. And the second derivative test is a rapid way for you to determine what kind of critical numbers you have. Now, before this test, you would need the first derivative test. In other words, you'd have to build out your increasing, decreasing table in order to know whether you have relative maxes or relative mins at your critical numbers. Second derivative test is going to be a rapid test that'll tell you pretty much right away what you have. Thanks a lot. We'll see you in the next video.